In the last class we have seen a relatively simple method for deriving shape functions for higher order triangular elements, and also we looked at concept of isoparametric mapping for triangular elements, and in today's class we will continue with that. So, here a 6 noded triangular element is shown, physical element, and also 6 noded triangular element, parent element is also shown. Usually any arbitrary physical element we are going to map onto a parent element as shown in figure B there, and the relationship between xy coordinates of the physical element and s and t coordinates of parent element is given by these relations isoparametric mapping x as x is equal to n1 x1 plus n2 x2 all the way to the number of nodes that we have for that particular element. Similarly, so using these two relations we get x and y, the coordinates of a physical element in terms of s and t. So, once we have these relations, we can write this derivative of shape functions with respect to s and t can be expressed, or they can be calculated once we know derivatives of shape functions with respect to x and y, and this relation can be compactly written as j times, where j is Jacobian, j times partial derivative of shape functions with respect to x and y, or the inverse relation if we know derivatives of shape functions with respect to s and t, how to calculate derivatives of shape functions with respect to x and y is given by this inverse relation. And so, one of the requirement is determinant of j should not be equal to 0, and determinant of j is defined like this. So, in the last class we have discussed some of the requirements like determinant, since it appears in the denominator in the above equation, it must not be 0 anywhere over the domain. So, the mapping is valid if determinant of j is not equal to 0 or the mapping is not valid if determinant of j is 0 anywhere over the element, and this requirement is similar to what we have seen for even quadrilateral elements. So, in today's class what we will be doing is we will take some examples and check the validity of mapping for triangular elements. So, this is the first example. For the 6 node triangle element shown below, develop explicit expressions for the isoparametric mapping and check the validity of this mapping. So, the steps basically are same as what we did for quadrilateral elements. So, first we need to write isoparametric relations of x and y in terms of s and t, and using those relations we need to take partial derivative of x and y with respect to s and t and find determinant of j, and one way is to look at determinant of j expression and see whether it is positive everywhere from s going over the entire domain. Here for triangular element s goes from 0 to 1, t goes from 0 to 1, or what we can do is we can plot x y in terms of s and t over the domain of the parent element and see whether the shape of the element is similar to what we started out, or if there are any folds then we can check for those. So, this is a 6 node triangular element, all the nodal coordinates are given, x y coordinates of all nodes are given. So, with this information we can write the x coordinates and y coordinates of all nodes. And then once we have this information, we can write using isoparametric relations, we can write x in terms of s and t, where shape functions or the shape functions corresponding to the parent element in terms of s and t. So, substituting n1 to n6, which we already found or which we already derived in last class for 6 node triangle element. Similarly, y in terms of s and t we can obtain using the shape functions of all the 6 nodes of the parent element in terms of s and t. So, once we have these relations, we can plot these equations of x and y for the range s going from 0 to 1, t going from 0 to 1. So, by giving different values of s and t and plotting the equations corresponding to x and y, we get this figure, and this figure shows a triangle which is similar to what we started out with. When this figure is compared to the actual element, it is clear that mapping is correct. Or we already know the relationship between x and y and s and t. Using that information, we can even find Jacobian matrix and determinant of Jacobian, and we can check whether this determinant of J is greater than 0 for all values of s and t between 0 and 1. So, it can be easily checked that this is indeed positive for all values of s and t between 0 and 1. So, the mapping is valid. So, this is how we can check validity of mapping, and also this is how we can get isoparametric relations. So, now let us take this example again, except that we move node number 4 and 6 little bit closer to node 1. So, the locations of nodes looks like this for the new element. For the 6 node triangle element shown below, develop explicit expressions for the isoparametric mapping and check the validity of mapping. And if you see what is the difference between previous element and this element, the only difference between this element and the one in the previous example is that nodes 4 and 6 are moved very close to node 1. We learnt earlier that the nodes, interior nodes should satisfy the condition that it should lie between L over 4 and 3 L over 4. So, once that condition is violated, that reflects in the mapping. So, that is what we are going to observe in this example. So, with this information of nodal coordinates, we can write isoparametric mapping expressions of x and y in terms of s and t, and once we have this, we can plot x and y for different values of s and t and see how the plot looks like. Or we can also find determinant of J and check whether it is greater than whether it is greater than 0 over the domain s going from 0 to 1, t going from 0 to 1. So, this is J, which is calculated from x and y, determinant of J, and this is plot of x and y xy expressions in terms of S and T, and you can see here a part of element is folded onto itself, thus mapping is not good. And this can also be verified by checking the Jacobian or determinant of Jacobian, and it can be easily verified that the determinant of Jacobian that we just calculated is not positive for all values of S and T between 0 and 1. For example, at T is equal to 0.5 and S is equal to 0.007742, Jacobian is 0. So, mapping is having some problem, it is not valid mapping. So, this is how we can check the validity of isoparametric mapping. And now let us go to the other concept, that is numerical integration for triangles. When we have integrals, especially for higher order elements, the integrals that we usually encounter are not going to be very simple integrals, sometimes we need to adopt numerical integration. So, we will discuss that now. So, integrals involved in higher order isoparametric elements usually cannot be evaluated in closed form, thus numerical integration must be employed. And recall that any arbitrary element, whether it is 3 noded or 6 noded triangle element, the actual or physical element is going to be mapped onto parent elements like this. If it is 3 node triangle element, it is going to be mapped onto 3 node parent element. If it is 6 node triangle element, then it is going to be mapped onto 6 node parent element as shown in the second figure. Whether a particular triangle element is mapped onto either of these, you can easily see these two, the vertices of these two triangle elements are located at 0 0, 1 0 and 0 1, and also S goes from 0 to 1, T goes from 0 to 1, and equation of the inclined side 2 3 or equation of the side 2 3 for both the triangles is given by S plus T is equal to 1. So, if one wants to evaluate an area integral over this triangle element, then the limits of integration are going to be 0 to, for limits for S are going to be 0 to 1 minus T, and limits for T are going to be 0 to 1. So, that is what is written here. Let I be the integral which needs to be evaluated, or this function needs to be evaluated over triangle area, and the limits of integration are 0 to 1 minus T, the limits of S, limits of T are 0 and 1. So, if one wants to evaluate this integral, it can be evaluated or it can be approximated in the way that is shown. I goes from 1 to m Wi times integrand evaluated at each of the integration points. So, one needs to know, if the order of integration is decided, one needs to know what are the weights and what are the coordinates of that particular order of integration, where Wi is the weight, Si, Ti are the coordinates of integration point, m is the total number of points that are selected, and the table below contains some information about the points and the weights, and also about the degree of accuracy of that particular order of integration. So, integration points and weights for triangles. So, if we decide to use one point integration, then we need to evaluate that at s is equal to 1 over 3, t is equal to 1 over 3, multiply integrand evaluated at 1 over 3 and multiply with weight half. If number of integration points is selected as 3, then we need to evaluate integrand at 1 over 6 multiply with weight 1 over 6 plus evaluate integrand at 2 over 3 and 1 over 6 multiply with weight 1 over 6 plus evaluate integrand at 1 over 6 2 over 3 multiply with weight 1 over 6, and sum up all the contributions from all the 3 points, then we get the final approximate value of that integral. So, this is how we can evaluate, and similar procedure can even be repeated if the number of points is selected as 4, except that we need to evaluate integrand at all the 4 points, coordinates of which are given in the table, multiply with corresponding weight and sum it up. So, now to illustrate this, let us take an example. Evaluate integral over triangular area n1 square plus n5 ds dt of a quadratic triangle element shown in figure below. For this kind of element, we already know this shape function expressions for n1 to n6. So, we can easily substitute what is n1 and n5 and simplify that integrand and apply numerical integration scheme corresponding to the triangle element and approximate that integral. So, for this particular element, n1 is given by this, n5 is given by this, which we already derived in the last class. So, substituting this information of n1 n5 into the given integral, I simplifies to what is shown there, and as you can see integrand is complicated. So, we need to adopt numerical integration scheme, and we need to identify what is the integrand. This is f as a function of s and t, which is given there is the integrand. So, depending on the number of integration points that we decide to use, we need to evaluate this integrand at so many integration points, multiply with corresponding weights and sum it up. So, let us start with one point integration. Integrand needs to be evaluated. Integration point coordinates for one point integration for triangle element is 1 over 3 1 over 3. So, integrand needs to be evaluated at that point, multiply with weight which is half, gives approximate value of integral. Next is 3 point integration. This is how integral is approximated, and evaluate the functions at the corresponding points, simplify, we get value to be this. We can even use 4 point integration, except that integrand needs to be evaluated at 4 integration points, multiply with corresponding weights and sum up. As you can see here, as we increase the order of integration, we approach closer to the exact solution. So, this is about numerical integration over triangle element. And now we will go and discuss the how to solve general 2 dimensional boundary value problem using 6 node triangle element. So, for that we need to first develop the element equations, and the procedure for developing element equations for 2D boundary value problem is similar to what we did for quadrilateral elements, or even for that matter linear triangle element. So, a 6 node quadratic triangle element with curved boundaries and its parent element are shown here. Physical element and parent element of 6 node triangle is shown, and the nodal coordinates of the physical element are identified as x1 y1 for node 1, x2 y2 for node 2, and so on. And we can put all the x coordinates and y coordinates of parent element in a vector. Vectors of x and y coordinates are defined like this, and for isoparametric mapping we require shape functions of 6 node triangle element in parent coordinate system, or shape functions corresponding to parent element. This is 6 node triangle element in parent coordinate system. The shape functions are as given here. So, we can put all the shape functions in a vector denoted with bold n, and now isoparametric relations. Using this we can find determinant of j, and once we have that we can find what is derivative of shape functions with respect to s and t. All this procedure is similar to what we are repeatedly doing for different kind of elements. So, once we have these derivatives with respect to s and t, we can find derivatives with respect to x and y. Derivatives with respect to x and y can be computed like this, which are denoted with bx and by. So, now using parent element shape functions, the trial solution and its derivatives can be written as follows. So, this is how T can be approximated. T is equal to n transpose D, where n is a vector comprising of shape functions of all 6 nodes, and D is comprising of the nodal unknowns or nodal parameters 6 in number, T1 to T6, and this is how we can get derivative of trial solution. So, once we have all this, we can substitute into the Galerkin criteria of general 2D boundary value problem. So, now let us look at what is Galerkin criteria, and we discussed this number of times earlier in conjunction with quadratic elements, sorry, in conjunction with quadrilateral elements and linear triangle elements. So, this is the Galerkin criteria for 2D boundary value problem that we are looking at. So, now we have the trial solution and derivative of trial solution. So, we can substitute that information into this equation and get complete element equations. So, substituting trial solution, derivative of trial solution into this equation and writing all 6 equations together in a matrix form, we get this, and we can define kx, ky, kp, k alpha, r beta, r q to write complete element equations as kd equal to r, similar to what we did for quadrilateral elements. So, now if you see here we have area integrals, that is integrand needs to be evaluated over triangular element area, and sometimes integrand needs to be evaluated over boundary of element. So, we need to discuss about integration similar to what we did for quadrilateral element for these triangle elements. So, evaluation of area integrals can be evaluated using Gaussian quadrature for right triangles. For example, kx is evaluated as, only thing is, since we are dealing with triangle elements, limits of integration goes from 0 to, limits of integration for s goes from 0 to 1 minus t, and for t goes from 0 to 1. With that understanding, we can proceed and get the number of or once we choose the, once we decide the number of integration points, we can get the points, coordinates and weights from the table that is given. So, S and T are the locations of Gauss point, Wi, Wj are corresponding weights. So, evaluating the integrand at the point, each of these points multiply with corresponding weight, we get, we can sum it up and get the approximate value of integral. So, to illustrate this, let us take an example. Evaluate matrix Kx for triangle element shown in figure below. Assume coefficient Kx is equal to 1 and use 3-point integration formula, and this is the 6-node triangle element that is given, and from the information that is given in the figure we can easily figure out what are the nodal coordinates. So, we can write all the x coordinates and y coordinates in a vector form, and that is the starting point, and also here it is suggested to use 3-point integration formula, and here we will the computations, computation details are shown for one integration point. So, similar procedure can be repeated for the other 2 integration points, and by summing up contribution from all the 3 integration points, approximate value of this matrix Kx can be obtained. So, x coordinates, y coordinates, and they work out the details, numerical details are shown here for one integration point, that is at s is equal to 1 over 6, t is equal to 2 over 3, that is the integration point that is selected, and weight corresponding to this integration point is 1 over 6. So, evaluate all the quantities at this point, partial derivatives of shape functions with respect to s, with respect to t, and then derivatives of x and y with respect to s and t. Then determinant of j. Once we have this, we can calculate what is by, and at this integration point, what is the value of this matrix is given by this. Complete ky matrix is obtained by performing similar calculations at the other 2 Gauss points, adding matrices obtained at the 3 points. Here there is a small correction, here In the problem statement it is given as matrix K x, but it should be Ky, and also coefficient is given as Kx, it should be Ky. So, with that correction, this is how we can proceed to evaluate these kind of integrals. So, now if you recall, these are the kind of boundary integrals that we need to evaluate along the element boundaries or element sides. So, now let us discuss about evaluating these integrals, these kind of integrals over a triangular element edges. The boundary integrals are evaluated in a manner similar to the one used for quadrilateral elements, and this is how we are going to map a 6 node parent element. Mapping is mapping to a 6 node physical element mapping to 6 node parent element is shown or is illustrated in the figure. So, edge or side 1 2 of physical element is mapped onto side 1 2 of parent element, and you can easily see that alongside 1 4 2 of parent element t is equal to 0 and s goes from 0 to 1. So, by substituting t is equal to 0 into the shape function vector, we can get the shape function vector along this side 1 4 2, and also please note that when we want to use one dimensional Gaussian quadrature, the limit should be from -1 to 1. So, we need to introduce another transformation or change of variable, and that will be illustrated as we proceed. So, consider evaluation of this r beta along side 1 4 2. So, r beta is given here, we need to evaluate this along side 1 4 2. So, that is the reason we are interested in finding the shape function vector along side 1 4 2. Along side 1 4 2 t is equal to 0, s varies from 0 to 1. So, by substituting t is equal to 0, the shape functions along side 1 4 2 are, we need to substitute in these expressions of n 1 to n 6 t is equal to 0. By doing that and putting in a vector form, we get this shape function vector. As you can see here, we need to here we can make another substitution, or we can define another variable as a function of s and simplify this vector further. So, in order to use one dimensional Gauss quadrature, integration limits must be from -1 to 1, whereas s is going from 0 to 1. Instead of that, if we define another variable which goes from -1 to 1. So, we are introducing a change in variable psi is defined as 2s minus 1. So, with this change of variable, the previous shape function vector which is rewritten here, when we make this substitution in terms of psi, this becomes this one, where psi goes from -1 to 1. That can be easily verified clearly. S is equal to 0 by substituting S is equal to 0 in the equation, psi is equal to 2s minus 1. We can easily check S is equal to 0 corresponds to psi is equal to -1, s is equal to 1 corresponds to psi is equal to 1. So, the limits of integration which are going are this, the edges or the side 1 4 2 is going from 0 to 1. So, we changed we used some kind of change of variables, and we so that we can get the limits from -1 to 1. So, in terms of psi we have the desired limits, and note that the 3 non-zero shape functions are one dimensional quadratic shape functions, and one could have and they could have been written directly using one dimensional Lagrange interpolation formula, because if you see along each of the edges the shape function of a node which is not part of edge, that edge is going to be 0. So, the non-zero shape functions are going to be the shape functions which are lying on that particular side or edge. So, those non-zero shape functions can easily be written using one dimensional Lagrange interpolation formula. Thus, integration along any side of triangle can be performed by simply writing quadratic shape functions for nodes along that side. So, now this side 1 4 2 of physical element is mapped onto side 1 4 2 of the parent element, and this mapping in terms of psi can be written like this: x is equal to n1 x1 plus n2 x2 plus n3 x3, because the rest of the shape functions are 0. Sorry, here it is n1 x1 plus n2 x4 plus n3 x2, and n1 n2 n3 or n1 n4 n2 are substituted in terms of psi here. So, this gives us relation between x and psi. Similarly, we can write relationship between y and psi, and we can take partial derivatives of x with respect to psi and y with respect to psi. And also we require the relationship between a differential element taken alongside 1 4 2 of the physical element, and how it is related to a differential element taken on side 1 4 2 of the parent element. So, the differential arc length on the physical element is given by d capital S is equal to square root of dx square plus dy square, and dividing on both sides with d psi we get the second equation, in which we can substitute what is derivative of x with respect to psi and derivative of y with respect to psi. So, this gives us relationship between differential element in physical element and differential element in parent element. So, with this relation the boundary integral can be written in terms of psi, which goes from -1 to 1, before we use one dimensional Gaussian quadrature. So, boundary integral can now be evaluated as follows using one dimensional Gaussian quadrature. R beta needs to be evaluated along side 1 2, which is defined as beta times n ds, and using change of variables limits of integration becomes -1 to 1, and differential element of the physical element d capital S is replaced with j times d psi, and this integral can be evaluated or approximated using one dimensional Gaussian quadrature by evaluating integrand at each of the integration points, multiply with weight and summing up contribution from all the integration points. So, this kind of procedure can even be repeated even if it is other integral. So, integral k alpha can be evaluated using same shape functions and Gaussian quadrature. Only thing is it looks like this, and here we discussed only along side 1 4 2, and if it is some other side everything is same except that different shape functions are going to be 0 along different sides. The procedure is same if natural boundary condition is specified along any other side. The only difference is that different shape functions are 0 along different sides. For example, along side 2 phi 3, the non-zero shape functions in terms of psi are these, which can also be, as I mentioned, which can, these shape functions can also be obtained using Lagrange interpolation formula. And alongside 3 6 1, these are the non-zero shape functions in terms of psi. So, to illustrate some of these details, let us take an example. Evaluate matrix K alpha for the triangle element shown in figure below. Assume alpha is equal to -1 for a natural boundary condition specified alongside 2 phi 3 of element, use 2-point integration formula. So, this is the physical element that is given. We need to evaluate this matrix K alpha alongside 2 phi 3, and from the information that is given we can easily write what are the shape what are the nodal coordinate vectors. Before we proceed, since we need to evaluate this matrix K alpha alongside 2 phi 3, we need to know the shape function vector alongside 2 phi 3 of the parent element, which can also be, or which can be obtained using Lagrange interpolation formula, or which can be obtained using the shape function expressions that we have by substituting S is equal to 1 0, t is equal to 1 0 at nodes 2 and 3, and by substituting S is equal to half, t is equal to half at node 5. Or they can be easily obtained using Lagrange interpolation formula. So, the non-zero shape functions alongside 2 phi 3 in terms of psi are given in this vector. So, K alpha is defined like this: alpha times n transpose needs to be evaluated along side 1 along side 2 phi 3, and this can be approximated with change of variables as -1 to 1 integral -1 to 1 alpha n transpose Jacobian times d psi, and which can be approximated using one dimensional Gaussian integration as it is shown there. So, now it is suggested to use 2-point integration, and this is just one dimensional integration. So, you can get the integration points and weights from the table that is given earlier for one dimensional integration. So, first integration point and weight are given. So, evaluate the shape function vector at this integration point and also rest of the quantities to calculate Jacobian, and then evaluate the contribution of this integration point to K alpha matrix by evaluating all the quantities in the integrand at this integration point, multiply with weight. Here alpha is constant equal to 1, and finally this is the contribution to K alpha from first integration point. Second integration point, coordinate and weight, shape function vector, and once we get the all other information, we can easily evaluate contribution of second integration point to K alpha matrix. So, we got a contribution from the first integration point, we got contribution from the second integration point. We need to add these two contributions to get final value of K alpha. So, K alpha matrix is given by K alpha 1 plus K alpha 2. Finally, this is the solution for this problem. So, this is the way we can evaluate these integrals using one dimensional integration along the boundaries of a triangular element, all the line integrals or the boundary integrals. And given any problem, once we have the area integrals and boundary integrals, we can write complete element equations and assemble the global equation system, apply the essential boundary conditions and solve for the nodal unknowns. And then once we have the unknown solved, we can come back to each of the elements and do post processing to find trial solution at any point inside the element and derivative of trial solution at any point inside the element. So, this completes higher order triangular elements.